Hi, everyone. Here is Tian Liu, and I'm here to do the homework 10, problem 1. And for this problem, we need to focus on the lecture notes to see the some definition and the properties of uh, these stochastic process. And for the first one, we need to find the Poisson process. And for the Poisson process, based on the lecture notes, let me check. Uh, we will have a definition of this one. We have we define the xt1 minus xt2 equals to the number of the call received in T1, T2, T1, and the probability of x t1 minus x t2 equals to k will be epsilon of the negative lambda uh, t1 minus t2 with the k of the lambda t1 minus t2 of the k. Yeah, and to uh, simplify it, we can define the T1 minus T2 into T, which will lead it to the negative lambda of T goes to K of the lambda T of the order of K. And I think this is its probability mass. And what we need to find next is mean. And from lecture notes, it's the mean will be the mean will be lambda multiplied by t, and also we can see that its autocorrelation is the rt1 t2 equals to lambda square t1 t2 uh, plus the minimize of the t1 t2, and yeah, just like the note state, it's uh, the mean of this Poisson process is very reasonable because with the longer time we wait, the expected number will be larger, and with this minimize part in the autocorrelation function, we will see it comes from the property of independent increments. And so that's it for the Poisson process. And for the next one is Poisson increment process. And based on the, let me check. Based on the starting with the PowerPoint of the process notes, stochastic process notes, page 12, we will see it's defined as there's exists the yt equals to uh, down with the epsilon and x t plus epsilon minus xt, and xt is a Poisson process, and then we can see its probability mass will be probability of yt equals to, upper with the epsilon, and it will equals to e with order of negative lambda epsilon multiplied by this one, right? And then we can see its mean will be or equals to the expected number of the yt, which will equals to the lambda, and its autocorrelation function will be yt2 will equals to, I think it's a separate function, I think. It's with different, yeah. So it will be separated into two parts, which first one will equals to lambda square when the absolute value of t1 minus t2 uh, is larger or equal to epsilon. And the next part will be lambda square plus the lambda over epsilon minus lambda multiplied by absolute value of the t1 minus t2, and the upper with the epsilon square, which have the t1 minus t2 absolute value less than epsilon. I think that's the autocorrelation function. And this increment process is to prepare for the next impulse process. And we can see if the epsilon goes to 0, uh, the impulse of the part of the lambda of the absolute value of t1 minus t2 will have it to the uh, have it to become an impulse with the area of the lambda. And for next part, we have the point impulse, Poisson impulse process, and this is on the Poisson impulse of the starting with the lecture notes, page 13, and we can have the definition of the zt equals to uh, derivative of the xt via the t, and the xt is also the Poisson process. And then we can see there is no actual probability mass function for it, but we can see the mean of day will be lambda, and the autocorrelation function will be the uh, lambda lambda square plus lambda of the impulse of ty minus t2. So yes, I think that's it for the impulse, Poisson impulse process. And uh, for the next part, we will have the semi-random telegraph signal. And for this one, we can check it on the lecture notes, page 15. And we can see it's defined as the kind of like the Poisson process, or kind of like the Poisson random variable. And we can see it defined as the also with the number of the something between the time interval equals to k, it will lead to the e of negative lambda t, excuse me, multiplied by This one. What about this one? And also uh, it has a definition of the xt, which the xt will have this condition. Okay, and the probability mass will be the probability of xt equals to 1, which will lead to the answer of the I think it's have the hyperbolic function answer, which is the epsilon of the epsilon of the negative lambda t with this triangle function. And for the probability of the xt equals to -1, it will be similar, but transfer this one to the sine part. Yeah, sine part of the lambda t. And these two are the probability mass function. And for the mean, we can see it's the expected value of the xt, which will lead us to the exponential of the -2 lambda t, and autocorrelation function will be d1 t2 y equals to the let me check. It's on the page 16, I think. Yeah, it will be the exponential up with the order of the -2 lambda multiplied by t1 minus t2. Yeah, I think that's it for the semi-random telegraph signal process. And the special part of this mean is that we can see it will mean will coming close to zero when the t is extremely large. Uh, so so it's like with the autocorrelation, we can also see that when the absolute value of the t1 minus t2 is large enough, we will have it goes to the zero, and it's like reasonable for us because the time interval is large enough. The two process will be more or less correlated. So that's it for the part 4. And for the part 5, we will do the random telegraph signal. It's on the page 16, and we can see uh, it's also part of the define the alpha as the random variable independent of the xt with the probability of alpha equals to 1 equals to probability of alpha equals to -1, which will lead to the 1 over 2. And we will have the yt equals to alpha multiplied by xt. Yeah, I think this is a definition of the random telegraph signal. And to find its probability mass, uh, it will be it will be like this one. Since I think the part of the yt as expand above, and we can see the probability of yt equals to 1, and it's equals to the yt equals to -1. y equals to the 1 over 2. And for the mean, we can see it will equals to 0. And the autocorrelation function will be RT1, T2 equals to the negative epsilon of the order -2 multiplied by lambda multiplied by absolute value of the T1 minus T2. And for this one, since the alpha definition is already taken that the probability of the alpha equals to 1 equals to the probability of alpha equals to -1, which is 1 over 2. So this part will be obvious for us to find out. And for the parsecs, we have to do the random work. For the random work, we can see it's like using the experiment of the tossing a fair coin. And with the tossing, we'll have this one with the x of the nt equals to the ks, which is the number of heads, minus the n minus k, which is the number of the tails, and multiply by this two, we will have the 2k minus n multiplied by s. And for this one, we'll have the probability mass equals to the xt equals to xnt equals to rs. Which will lead to this one. I think it will be the chosen n from the chosen n plus r over 2 from the n, and multiply by 2 2 with the order n with the 1 over it. And from the lecture, from the page 18, you can see the mean t will equals to 0 because it's finding the expected value of the xt. And we can see the autocorrelation function of this one will equals to let me check correlation function. Oh yeah, it will equals to the expect value of the xnt multiplied by xmt equals to the minimize of the n and m and multiplied by s squared. And for this one, we can see that from the probability mass, we can see that if n is large enough, we'll have something like the Gaussian. And for the correlation part, it's also have the main part of this one, which is comes from the property of the independent increments. And here comes the last part of it, which is the Wiener process. And for this one, we can check it from the page 20 of the notes. You can see we define a thing of the WT, which equals to the limit. This limit with the S to 0, T to 0, and n to infinity of the xt, and uh, xt is the random walk. It's not a Poisson process, it's a random walk. And for this one, we can have its probability mass will be okay. So this probability, I think we only have the density function of this one, which is well equals to the density function y equals to the 1 over square root of the 2 pi alpha t, and multiply it by the exponential value of the with order of the negative 2 alpha t with the w square. And also we can see that the mean of the t with the w is equals to the x-bar value of the wt, which will lead to 0. And the autocorrelation function of this one will equals to the uh, minimize of the t1, t2 multiplied by alpha. And for this one, we can also see that it's in the autocorrelation function, there's a minimize t1, t2 comes from the property of the independent increments. And I think that's it for the problem one. And thank you.